Hi, Varun.
Okay. And I didn't ask, but is it okay to post the your recorded video in YouTube?
That should be fine.
Should be fine. Okay, good. Thank you.
You can see the slide, right?
Oh, not yet.
Oh, really? Okay.
You can see the slide, right? Not yet. Oh, really? Okay.
Yeah, it's slowly showing up.
Okay, okay. All right, so I'll stop sharing now, and when you ask me to, I'll start it again.
Okay. Very good.
Varun, you let me know when to start, right?
Hello? Yeah. Hello?
Yeah, Varun,
Are you able to hear me?
we can hear you. Yes.
Yeah. Hello? Sorry, some issues
Hi,
at my
Varun.
end. Yeah,
Yeah, we can hear you.
we can get started. So welcome to this ECE webinar, and today's talk will be given by Professor Dipanjan Gope. He's an associate professor in our department, and he's also a co-founder and CEO of Simyog Technologies Pvt Limited, a spin-off from IISc, which is focused on design and sign-off tools for automotive electronics. And his research interests lie in the areas of computational electromagnetics and electromagnetic design and automation. And he has also worked, or he has been a founding member of a few other startup companies which have been acquired by other major players in this industry. And before that, he received his master's and PhD from University of Washington, Seattle. With that introduction, I will give the presentation to Dipanjan. And if there are any questions, you can either raise your hands or you can post it in the chat box. And we can either take them in between the talk or the ones in the chat box, we'll take it at the end. Okay, thank you. So over to you, Dipanjan.
Yeah, thank you, Varun. Just if you can just confirm that my slides are visible.
Yes, it's not in slideshow mode yet. Yeah, now it's good.
Okay, awesome. Thank you, Varun, for the kind introduction. Without any further ado, I'll get started. So what I want to talk to you about today is system-level EMI EMC simulation and how we can apply machine learning techniques to enable this simulation. First, in addition to what Varun said, because it's an online presentation, I'm a faculty at IISc, also co-founder at Simyog. For some of you who are joining outside from Bangalore, this is where we are located, and that's our institute. My personal background is in computational electromagnetics. I'm actually relatively new to EMI EMC area, although I have been working here and there in EMI EMC. It's only in the last 5 years that that I've been looking in depth in EMI EMC simulation. Set of acknowledgements first. The work that is presented here it's been performed with several people, financial support, technical support, and other support from several folks here from Panasonic, Denso, DRDO, RBI, Cypress, and Simyog. So I'm, to an extent, I'm a messenger of some of the results that I'm going to show you here. So this is the outline of my presentation. I intend to close the presentation in 45 minutes. I have 100 slides, so I'll see how I do. And then take a question and answer in the last 15 minutes or so. In this presentation, I want to touch upon why EMC, right? I'm, so to say, also an outsider to EMC. I've been only working on this for 5 years. but what attracted me to EMC and to solving some of the problems in EMC, I'll talk about that. Then what are the challenges that EMC poses to system integration or electronic system design and manufacturing, whether simulation can be an appropriate solution to that, what is the current state of EMC simulation, and that will bring us to the topic of machine learning as an enabler for EMC simulation. I am on slide 5, moving on to slide 6. So if you follow the hardware progression of over the last 5 to 10 years, what you would see is that the chips are getting embedded into electronic systems, PCBs in general, and these PCBs are sitting inside bigger systems like super systems, which we now are now call systems. And automotive is an example of this. I mean, you've all heard the terms of IoT, sensor networks, 5G, etc. Those are horizontal fields. To me, one of the examples of perhaps all of that is in automotive, with the trends like safety, connectivity, ADAS, automated driving. What is happening is that the bill of materials of an automotive is crossing 50%. What that means is, if you look back 15 years or 20 years for that matter, the raw material going into an automotive, which is called the bill of materials, would be 5 to 10% max electronics and hardly any electrical, maybe some electrical. Now it's around 30%, and with electric vehicles, it's moving around 50 to 60%. So we have to sort of reimagine the car as whether it's a mechanical device or an electronic systems device. There are challenges that comes with this, right? And this is just an example of systems that are there, right? So just to explain, semiconductor lies at the as a horizontal. On top of that, we build electronic systems. Electronic systems itself has, typically we say 5 or 6 different verticals like automotive, aerospace and defense, and IT-com, industrial, medical electronics, right? So these are the verticals on electronic systems. And if you look around you in the room that you're sitting in, you'll probably find a lot of electronic systems like the ones that we are talking about, right? Even if you look at a mundane object like a toaster, right? They are now equipped with alarm, etc. So you see a lot of electronics, connected electronics that's coming into systems, which is causing some issues, right? Which are causing issues of interference between these electronics or electronic systems in the system level design. The main reasons are high packing density of electronics, right? You would see that in sensor networks or so, also seen in things like aerospace and automotive. The power electronics, which is there in most of these systems, that converts your wall charger to 12-volt electronics for the car or for the electronics to run, they are running at higher and higher frequencies or higher switching rates. The reason for that, you want to make these power electronics compact, so the inductance and the capacitance that you put in, you want to make them compact. For that, higher switching is actually better, right? So this is something that's also causing further emissions or interference, right? And of course, high-speed communication. Ethernet in automotive is fairly new. And we are looking at 10 Gbps Ethernet in automotive soon. So all of this, what it leads towards is that unintended behavior of electronics in general, right? So for example, right, let's say I am making a tire pressure sensor, and a tire pressure sensor, let's say, works very well in the laboratory. Everything passed, but then when you go and integrate it inside the car, you find that it's failing, right? And the reason for that is the interference from other electronics is causing issues for that particular equipment, right? Electric vehicles is another example of a place where such interference is actually exaggerated, because it's like electric vehicles, at least the battery part of it or the power integrity part of it, is basically the similar power integrity that's there on your PCB, but at much higher voltage rates, right? So you have a battery that's feeding in around 300 to 400 volts, and typically most electric vehicles operate with induction motor these days. So there's an inverter, and then at the charging station that may be at a different voltage, and the 12-volt electronics is at a different voltage. So there's DC-DC converters and inverters that are switching fast, and their emissions can actually hinder the car antenna and the car ECUs and so on, right? I'll show you some instances, right? These are actually problems that cause problems in the industry, and most of it, as it should be, are taken care inside. Some of it comes out. I'm showing you some of those documents from newspapers, right? The Toyota unintended acceleration problem in 2014 was a big issue, right? That was later diagnosed to EMC. It was found in 2010 that an electric vehicle would shut down in front of a Walmart or something here, right? That's for emissions. If you look at this document from Tektronix, one of the key challenges that they put out for IoT, implementing IoT, is this interference, this EMI EMC problem, right? So that's what attracted me to this field. And in EMC, right, the way we classify EMC is this by 2x2 matrix, radiated and conducted. This is based on how the propagation is happening. If the propagation is happening through air, it's called radiated. If it's happening through copper or harness, it's called conducted. And there are two forms of goodness of a design under test. One is emission and another is immunity. Emission means how much are you hurting others, which means how much are you affecting others. Immunity is how much are you getting affected by others, right? So this is sometimes also captured in the form of susceptibility, which is the opposite of immunity, but has the similar terms and numerical measures, right? So if you combine this 2x2 matrix, what you end up getting is radiated emission, conducted emission, radiated immunity, and conducted immunity. These are typically the parameters that we test for any electronic system before it can be embedded into a super system or in the system level design, right? And I will talk more about this in the coming parts, right? So what are the challenges that ESDM faces from EMC? I'll show you one of them, right? And I will, I'll identify two major problems. And the last one I'll identify as my last slide. So it's towards future work. The way this is solved today, right? So, you can question, I see a lot of electric vehicles out there on the road, then how are they operating, right? So the way we take care of this is that, typically such a complex system as a car has multiple players involved, right? So you start with the IC manufacturer like NXP, TI, etc., right? And then there are this tier one, which is the electronics components providers like Bosch, Denso, Continental, and so on, right? And then on the top there is the OEM like Toyota and Volkswagen and Tesla and so on. Actually, Tesla also makes their own components, so they fall in both categories, right? So let's say you're Toyota and you want to make a new car. You give the order of making the electronics to the tier one suppliers like Denso, and the tier one supplier will buy the IC from NXP or TI and then make the product and ship it to the OEM. Now, the way the problem is solved today in the industry is that at every level they have to pass EMC tests, right? So IC manufacturer has to pass IC level tests. The tier one has to pass component level or bench level tests, and then finally it gets integrated. And the assumption is, which has been working well so far, right? Assumption is that if you're passing the test at every level, it is likely that you're going to pass it at the system level as well. This is sort of a pessimistic design process, but you're basically, kind of creating limits for every equipment to radiate or conduct, right? And in order to meet these challenges, of course, you're putting in extra components in the system. So it's actually bears costs associated with it, right? So we will see what the problem is. This is how the industry operates today. So just to give you an example, right? This is an example of a conducted immunity test where this is a touch screen controller from Cypress, and the idea here is that you see that a lot in automotive infotainment systems, for example, today. This test board, what the functionality of this test board is that if you press an LED here, if you press a button here, this LED is supposed to glow, right? It's a capacitive touch. So when you press the button here, the IC is sensing the capacitance, change in capacitance, and then therefore just triggering an LED. It could be triggering something else in the infotainment center and so on. What is happening in this test is the stress test of this particular PCB is that you are injecting some noise onto the cable. This cable would be there in the system level design, right? So you're injecting noise into this cable using a clamp, right? An artificial clamp, and you can see that the LED is actually glowing, which means that there's nobody touching it, but the LED is glowing, which means it's a false touch. It's an EMC failure event, right? And that's what we are trying to work on, right? I'll tell you what we are trying to work on in just a little bit. So what happens is that, these are some of the tests that needs to be passed in order for the tier 1, for example, to qualify to sell to the OEM, right? So you have your own stringent limits and you have to pass that in order to sell it, right? So the challenge that's happening is that you're taking it to the laboratory, but the first time, around 50% of the devices are failing. And even in the second and third iteration, you're failing, right? So this is quite different from what happens in the semiconductor industry per se, right? In the semiconductor industry, like Intel, NVIDIA, etc., when you do for a tape out, you're pretty much certain of how it's going to behave. Here, because this is a laboratory test, you have to make a sample. And if you fail the first time, second and third time, you have to make second and third sample. And that's adding 6 to 12 months to your design cycle. What means that you have a product, let's say January 1st of 2021, it's working very well, but you cannot sell it till January of 2022 because you're not passing this compliance, right? So it's an opportunity cost more than anything else that comes into the picture, and we are looking at how to make it pass the first time round, and that's the motivation towards simulation, right? So our objective here is that this is what's happening today, which is multiple lab testing with a prototype starts at the very end of the design V cycle, right? Typically around this part, you'll see a design. You would see a prototype has been made or a sample has been made, and after that, several different samples, and then you try to pass. It's quite a challenge, right? And the idea or the solution to that, what you would think from common sense as well, is that we would want to do these iterations at the early stage of the design cycle, such that January 1st, 2021, first time you make a sample, it passes in the laboratory, right? So this is our final objective, right? The holy grail in this particular problem. In order to do this, you'll have to enable a full system EMI EMC simulation, and that is a challenge today. It does not exist. I'll tell you why. What are the advantages of doing it at the pre-prototype? Is it just passing, etc.? It's much more than that. Actually, you can, what happens in the early part of the design cycle, right, is that, several new requirements can come in, right? So, somebody can say, if you add this component, if you add LTE to this system, or, if you add 5G to this, it can do these more functionalities. So typically a lot of inputs are coming to the design guys while this speccing and designing part of it, right? So to that extent, in software, what we do is a process called agile, right, where you can take in feedback on a daily basis, etc., and can put it inside your software. Such a process cannot happen unless you have the simulation capability in the early design cycle, right? So for example, one of the key things here is the cost and weight reduction, right? In particular for drones, etc., you can imagine that weight reduction is a big critical issue, right? How do you reduce weight? You reduce some of the metallic parts. If you reduce the metallic parts, then there is more interference, right? And therefore, to enable cost and weight reduction, you need EMC simulation capability at the beginning, right? And so the first time we touch upon the subject of this presentation, which is IC models. The reason today there is no EMC simulation, no pre-prototype EMC simulation available in anywhere is because of the non-availability of these IC models. And I'll explain more as I go ahead. So let's talk about the current state of EMC simulation, right? So I'm on slide 21. I'm looking at the different simulation techniques that have enriched the electronic system and semiconductor industry for a while. Circuit simulation, actually, this originated from a class project in Berkeley from Professor Ron Rohrer's laboratory, then got into Cadence and Synopsys. Now every company has a circuit simulation tool, right? Intel has, not only the EDA vendors, but every company like Intel, TI, NVIDIA would have their own circuit simulation tools, right? So again, starting from an academic project. Signal and people trust it, right? Now, people don't say that circuit simulation is not going to match your results, your measured data, right? That's the golden data, right? Measured data. Everybody believes that circuit simulation is going to match that. Now, signal and power integrity, sort of a little late into the game, which is 1990s to 2000. Because the switching, because the SERDES and other phenomena, we've been looking at SI and PI, right? And now it's commonplace, right? So when I say commonplace, if you go and ask a signal integrity or a power integrity engineer whether simulation is going to match measurement, I can guarantee you 90 to 95% will say yes. Such is not the situation with EMI EMC. Right? If you ask the experts of EMI EMC, I would say 5 to 10% would say simulation can match measurement, right? And there are some reasons for that. So let's take a look at how would you simulate EMC. So this is a radiated emissions chamber, right? And this is a very small DUT, a test DUT, so it's a crystal oscillator and a microstrip, and this is this is basically connected to cables and fed into the LISN. And so on, and there's an antenna that you don't see here that's actually finding out what is the radiation from this system, right? So how do you simulate this room or this room with this DUT? Well, it's not that difficult actually, right? It is, basically what's happening is, where is the noise coming from, right? It's actually coming from the ICs. The ICs are switching. If you take a DC-DC converter, that's one of the key elements of switching today. If you take, for example, a microcontroller, a CAN driver, because of the switching in the circuits, it introduces some noise currents into the system, right? And then the noise current actually travels through the channel. In this case, the channel is the cable, the DUT, the PCB tracks the cable, and then the LISN, and actually returns through the chassis, right? And in making this loop, or in making this transfer or propagation, this red dot, right, or this current is actually generating the EMI, right? So what do you need to know then to solve this problem? Well, you need to know how big the arrow is. That means what is the current signature? What is the signature of that current? And then you need to solve for propagation, right? And when it comes to propagation, I think in the industry and academia today, we have quite a mature technology in terms of 3D electromagnetic solvers and all that. What is missing is that this switching, the model of this switching inside this IC is not present in the industry today, right? So we are working on some interesting methods on how to do that. I'll tell you why it is not present also in a little bit of time, right? So what do? Well, if the current is known, then we do a current density plot, right, on top of this, on top of the system. This is the top view of the laboratory, right? We do a current density plot, and once the current density on the entire structure has been found out, you can actually post-process and find every other quantity, like radiated emission, as is shown here, also conducted emission, and so on and so forth, right? So this part of the problem is okay, right? And if the IC models are available, then I believe that pre-prototype EMC simulation will be commonplace, right? And that's what we are looking into. The IC model, so you can see the problem. If the IC model is not known, you have a transfer function. Let's call that H of F, and you have a X of F, right, which is what the current is injecting. At the final end, there's Y of F. The H of F is actually commonplace. I mean, you can compute that. It's hard because it's an entire room level simulation, but the transfer function is actually well known. So what you're really looking for is characterizing this X of F. And if you don't have X of F, if you only have H of F, right, you really can't get an idea of Y of F, right? You can do what if analysis, but what's the advantage of doing what if analysis if you do not know exactly whether you're close to failing or close to passing, etc. Right? So the actual level of EMC will not be known today in pre-prototype system level integration. So therefore, pre-prototype is not possible today, and that's what we are looking at. So primarily two reasons why this is not there in the industry today. One of them is time and memory efficiency of the propagation simulation, right? There are great tools available from ANSYS, Dassault, and others to do this. But, it is such a complicated problem in the sense that the size of the matrix that we have to solve is quite large. It takes a lot of time, and with the complexity of the cables, if you have twisted cables, if you have PCB with multiple layers and all that, right? So this becomes quite hard, but still a solvable problem given, let's say, 512 GB of RAM and so on. But the lack of models is a showstopper, right? And that's what we are looking at, right? At solving, right? So the method that we are following here is a combination, therefore, of physical science and data science, right? Which is the physical science part of it is the propagation part of it, which is where I have been working on for the last 20 years, which is fast 3D electromagnetic solvers, or some solvers that would give you the actual behavior of the electric and magnetic fields. Basically, at the end of the day, the physical science solver is solving Maxwell's equations, right? But today's topic of presentation is more in the lines of this part, right? So what we are trying to do is to reduce complexity on the physical science solver. We are building models of different parts of the laboratory, and in particular IC models. That's a showstopper, right? And why are the IC models not supplied by the IC vendor itself? I'll come and talk about that in a bit as well, right? So we are using a two-pronged approach, and the talk today is focused on the data science aspect, how we are generating IC models and where the future of this lies. So, we will get to the data science part, but, I have 5 slides on the physics-based solver so that, you don't miss out on the physics-based part. I usually don't show equations, but Maxwell's equations is something that we cannot go without showing in a computational electromagnetic talk. So here it is. This is Maxwell's equations in the time domain. You can see that, and it's in the differential form, right? And you can represent Maxwell's equation in time domain or frequency domain, differential form or integral form. The different solvers that are available today will be a combination of this. So for example, HFSS from ANSYS is a frequency domain differential form solver, right? And for example, CST, which is from Dassault, it's a time domain and a differential equation solver. In my laboratory and at Simyog as well, we work on integral equation solvers in frequency domain, right? So the idea is that whatever form of Maxwell's equation you use, you should get the right answer, and the right answer is the one that is measured, right? So only that you're doing it earlier than actually having a prototype to measure. Right, so this gives you an idea of the EM solver methodology, as we talked a little bit about. FEM is using differential and frequency domain, FTTD using differential time, MOM using integral and frequency. There are advantages and disadvantages to solving to all these methods. Some methods are applicable better there, some methods elsewhere, right? In this particular method, I found that MOM has a good application because in MOM or in partial differential or integral equation based approach, you actually do not discretize the entire room. You can only discretize the structure, which is different from in FEM where you have to discretize the entire room, and therefore the size of the problem can be prohibitive, right? So, but I'm pretty sure that with advanced FEM methods also you can address some of these RE challenges. Right? So how do we solve this? How do we solve propagation problems? Well, if it was a cube, like let's say if the channel was a cube or a sphere, right? I could solve Maxwell's equations on a piece of paper, right? Because the integrals and the differentials you can actually compute very easily on if the coordinates separate, right? So on an orthogonal coordinate system, it is quite easy to do. But unfortunately or fortunately, most of our systems are arbitrarily shaped 3D geometries, right? So what we do is first we divide it. It's a multi-agent sort of a problem, right? You basically divide it into small agents, in this case called basis functions, right? And then these agents or basis functions will have to interact with each other, obeying the Maxwell's equations, right? And that gives you the matrix formulation that every, it cannot be that the charge density here can be high or this one low, completely ad hoc. It has to be as per the Maxwell's equations and boundary conditions, also as per Maxwell's equations, right? So at the end of the day, you're solving a large matrix and this matrix can be of the order of 10 million dense matrix. So you can think of a 10 million dense matrix, how much memory it is going to take if you store it as a complete matrix. So this is a subject of a different talk. I'm going to skip that and get into our approach right now. We have some fast solver physics that takes care of the compression of the matrix. That's the physical science part, but I'm going to skip that. Today, thanks to the work of the last 3 decades, we are able to solve it in order n log n time. Right, but then now let's talk about IC models. What are the challenges of the IC models? Right, first thing is that the semiconductor vendor, right, has his own IP built into the IC, so he cannot really release the entire SPICE deck, so to say, of the IC, right? And although IBIS has been there for a while, so SPICE file is ruled out, right? So SPICE file will give you all the internals of an IC, and if it's a digital IC, then SPICE file, which is really for analog simulations, is just not manageable, right? SPICE can handle up to probably 1 million, 10 million transistors. Beyond that, it's hard to handle for SPICE itself, right? So digital design doesn't even do SPICE, right? So then what is the model definition? The first question is, how do you define the model itself? So till date, so SPICE is one of the models. Next model is IBIS. IBIS has been very successful in doing signal and power integrity, and later power integrity, signal integrity in the beginning. But EMC model standards itself are not that very well established, and certainly not at an industry level. It hasn't been demonstrated with success. So let's talk about what standards there are today in IC models, right? So these are the IC standard 62433. Again, it came from an academic background. I think starting from 2000, some groups in University of Toulouse, France, they were working on this, and then now many groups are working on some of these standards. But these are, as you can see, these are standards. So several years of research, and then this has become standards. There is an immunity model called ICIM, and there's an emission model called ICEM, and I'll explain what that means. Right. So let's say we are taking, we are trying to solve this problem where you have, a termination, a cable, and the cable leading to the PCB, and the IC is sitting on top of that PCB. Now, how do you model this IC? I don't need to really know what's happening internal to this IC. As you can imagine, the current will face some hurdle when it's entering this IC. That hurdle we call impedance, right? So an impedance, and then there's another thing called immunity behavior, which is, the IC will be able to withstand some amount of noise on its pins. But if you cross that level, then it will fail, right? So that level is called the immunity behavior. So ICIM proposes that you have the impedance and the immunity behavior inside the model, right? And we have looked at this, we have extracted these models, and we have published some work with the Denso that, that we are actually able to solve this immunity problems. Solve means we are able to predict the immunity problems before if it's going to happen. Right, before a prototype. This is, of course, you see the actual prototype where there is a failure happening in the IC. And so first what we do is do the measurements. You see that these are these are the failure levels in the different frequency regions, right? And the question is whether you can predict it with the help of simulation. Here, for example, we are using a static model. Right, the machine learning use comes in when you're looking at the dynamic models. I'll talk about that in the next few slides. But so this is a model, right? So this is the S parameter, or the impedance of the IC pins. That's part of the model, and the interesting part is this part, which is the immunity behavior. It's almost like a limit line. For a given frequency, if you stay below this levels, you will pass. If you cross it, you will fail. So the first thing we did was we generated the immunity behavior, or the model of these ICs, and then we did a simulation, and then we found that the noise that's reaching the IC is exceeding the limits at the places where the measurement failed. So although this was done after the fact, the idea is that this gives confidence that if you are able to simulate the noise on the pins and predict the noise levels, then you will actually be able to predict the measurement failures at a stage where the device is not yet existing. So how do you do this simulation? Well, there are, you have the PCB is typically available in the form of an ODB++ file or a Gerber file, right, that you can import and basically do that electromagnetic simulation on top of that. Right, and we have done it for several different conditions. All of that worked well. We talked about the Cypress problem. That also we were able to predict well. In this particular case, the red line is the immunity behavior. This is the actual PCB, and this is the PCB in simulation. Right, these are the layers of the nets and the layers of the PCB. The red line is the immunity behavior, and the black line is the noise that's reaching the pin of the IC. So wherever the black line is crossing the red line, it's a failure, right? And here, actually, there is a failure. The black line isn't crossing the red line. We believe that there's some capacitor model, etc., mismatch. This black line should have actually crossed the red line here, right? So that's some of the work on immunity. Let's talk about emission, which is this IC now is happening the reverse way. The IC is injecting some current into the system, and that current, when it travels through the harness and all that, it's emitting to the antenna, right? So basically, it is the model itself is comprised of the switching frequency or the switching points of the IC, which we talked about, right? We are able to do quite a bit of correlation, right? This is the duty that I talked about. This is the duty with the crystal oscillator and all that work done with Panasonic. Osaka, right? This is the measurement versus simulation correlation of that. This is the RE problem that I mentioned earlier. This is the simulation versus measurement correlation of that. Typically, we aim for around 6 dB, right? Although it seems like quite a big difference, but in EMI EMC, because of so many uncertainties, 6 dB is a good measure of correlation. This is a DC-DC converter in conducted emission setup, and this is the simulation versus measurement correlation. This is set in radiated emissions, and this is the simulation versus measurement correlation. And this is a Cypress touch screen, right? You see a lot of these equipments in the car. This is the touch screen itself. The touch screen geometry is like this. There is a PCB controller to the touch screen. Basically, wherever you press with your finger, right, it's this IC is trying to detect where you pressed and therefore do some inference, right? And you can see the correlation here as well, right? So now coming to the main topic finally, right? All the simulation results that I showed you earlier, that's based on models where the model was generated with the same operating condition as the measurement, as the RE and C measurement. Now, let's think about this for a minute, right? Now, you are trying to generate a model of the IC, and this model is actually a switching waveform, and it is a function of several operating conditions. In fact, it is also a function of the PCB that it's sitting on. So it's kind of non-intuitive that way. You try to build a model such that you can sort of black box or abstract what's inside it. What if what's inside it is also dependent on what's outside it, right? So that becomes a really challenging problem when it comes to black box modeling or such IC model generation. Just to give you an example here, this is a DC-DC converter model. This is the frequency domain representation of that. At a switching frequency of 100 kilohertz, this is how the switching noise looks like. And at a switching frequency of 125 kilohertz, this is what it looks like, right? So, most of the times you will not know the physics of internal part of the IC. You'll have some idea, of course. So this is a classic example where we are actually not doing a research in machine learning, but we are doing a research in application-dependent machine learning. All the machine learning tools that we have used are off-the-shelf tools, apart from the feature extraction part, because that becomes critical and application dependent. So for example, if I pose to you this problem that, can you predict this blue image, and that, if I change my frequency, it will become the black image, right? And this is just 2 of the parameters. You have 5 different parameters and several sort of values of those parameters, and things can change, right? So you're basically trying to predict an image, so to say, given several parameters, and that became quite a challenging thing. We have some solution, we believe, today, but it can, of course, certainly be improved beyond that, right? So the biggest, contribution, so to say, for here was the feature extraction part. Is one thing is that, I mean, the naive thing to do is to say, let me divide this image into pixels and let's just predict the RGB values. You'll have a million unknowns to predict, right? So that is not possible. So how do you do feature extraction such that, you know, you can only need to predict some parameters or some features, right? And you can get the rest of the network, you know, easily. Right. So first, let's talk about what the model is. So this is a schematic diagram of an actual DC-DC converter with an IC sitting on it. Now I'm going to replace this IC with its model. In this case, we have used what is called a 2-voltage source model, right? And the 2-voltage source model we have found behaves exactly like the IC if generated right. Right, but imagine this, the values of these 2 voltage sources will be dependent on parameters, and that's what we are trying to figure out using machine learning, right? As a parameter changes, how does that change? Because although, you know, even if the SPICE was available, even if the internal physics was available, I believe this, you know, data-driven approach is probably a better approach, because, you know, it just saves a lot of time and computation and a lot of, you know, very expensive simulation. Right, so you just learn from the data, you know, and in the learning process, physics will always help you, because, you know, it'll tell you what the feature extraction should be, etc. But perhaps there is a way where you can combine the physics with data science here, right? So just to give you an example, here is a mock DC-DC converter. You have two sort of MOSFETs, switching MOSFETs, high side and low side. And now you're replacing that with 2 voltage sources, the values of which depend on these machine learning parameters, right? We have done this for several different operating conditions. So you can see what the operating conditions are here: the voltage, the switching frequency, load current, and the cable parameters. I'm going to flash some slides in front of you. Basically, all of them will be curves on top of each other. The reason that I want to show this to you is that the model is exactly the same as the actual IC, right? So we did the simulation or measurement with, the simulation with the actual IC, and then we did the simulation with the model. These are all sort of on top of each other. We are probing different test cases. We are probing different points of the IC, right? So, but the big challenge is that the VSW and VN, which are these waveforms that can change with the operating condition. So this is our prescription in terms of the machine learning. So what we do, let's say if I have to generate a model of the IC, and let us say that SPICE is not available. So we make a PCB where the operating condition of the IC can be changed, right? And then the first step is parameter identification, which is what are the parameters that are actually affecting the IC model, right? I think that would be fairly straightforward to do, and we'll tell you how we do that. And then after that, we have to do the DOE, the design of experiments, so that we can generate the training set. And after that, this is the part that is very critical, which is the feature extraction part. And after the feature extraction, then you can do the network training. Here we have used multiple different networks to train different features. That can be done differently as well. So once this network is trained, the network itself becomes your model, right? So that anybody putting in different values will get the model out of that. So that's the process. We can do it with SPICE simulation as well, but sometimes we have found that the SPICE simulation does not match the measured data, right? So measurement is the golden data. So, you have an IC, let's say you want to generate a model for that, because you're going to use that IC in the next 2 years of your development. So you make a PCB that can change the operating condition of this IC. You make a lot of measurements, around 300. We have 5 parameters, and then feed it into neural network and get this results out, right? So talking individually about each step, first is the parameter identification. It is not as complicated that it looks on this slide. It's basically what we do is, we identify some of the parameters. Again, here physics can help. Otherwise, it'll be a hard task, right? Based on your physical judgment, right? You identify some of these parameters that can have an effect or can change the IC model. Then you basically go from min to max and see whether the result or the sensitivity is high. So for example, again, I'm going to flash some slides in front of you. This is just to show the min and max response. And if the min and max response is too different, then we say it's a parameter. Otherwise, we omit the parameter, right? So these are several such things that we have used. And then after the parameter is extracted, then you do DOE. We have not done too much research on the DOE. We use a method called box Benken, which is basically nothing but the corner points and the middle point, in order to generate the training set. And then this feature extraction, this is where a lot of thought has gone in and all that. We do the feature extraction, not in the frequency domain, but as you probably suspect, in the time domain. But different parts of this waveform are predicted, right? So the rise time, the fall time, the ringing, both sides, like on the upside and the downside, both of them are predicted. And then from this, after predicting all of these features, we can reconstruct the time domain waveform and then go to frequency domain. Interestingly, right, 2016 we had done sort of the reverse work with when Nikita was pursuing her PhD, right? So all of that came back to us when we came across this problem. Here is a different problem, actually predicting the frequency, but we found out some of the same techniques actually, or similar techniques actually worked, right? So this is some of the ANNs that we have used. We use very simple ANNs, right, in terms of fitting, right? So let's say rise time is one of the parameters. We would use a simple, probably 3-layer. I'm not sure exactly how many layers the network was, but so these are some of the fit results: the rise time, fall time, and we have predicted the network error. Different topologies are used to predict different features. And then once you get that feature, then we have compared this. This is the FFT, the frequency domain response. What is important is the envelope of this, because that's what's critical to us. So the blue and the red, these are measured data, and then the model fitted data, right? And then basically you publish this model itself, or the neural network, or the set of neural networks as the model itself, right? So I'll show you an example. This is an LT8641 IC. It's from Analog Devices. We purchased this IC and made a PCB to actually change this, change the operating conditions. And this is the schematic diagram of that design. And then this is some work done by Suraj, Anand, Leela, Bibhu, and others, right? So this is the measured waveform, right? So you see the red line, I believe, is the measured data, and the blue line is the ones that are coming from simulation, right? From SPICE. This actually shows you that SPICE sometimes may not be that accurate. So that's why we move towards using measurement-based data, or measurement-based training, right? So these are some of the correlation results. Again, several test cases. This is the measured data, and this is the simulated data. What I can say is this is one of the first times that people are actually trying pre-prototype EMC, right? Although this has been done after the measurement was done, but this shows the capability of doing pre-prototype EMI EMC, right? These are obviously different cases that we have to study in order to actually know that your model is working at the different conditions, right? So that brings me to my last slide, right? Where is the potential for machine learning in such a field like EMC? I think it's a huge potential. I mean, I think the industry will love this if we are able to do and solve this problem of pre-prototype EMC. Today we have done DC-DC converters, some PMICs in ICEM in the emission domain, right? So there are a lot more ICs, right? Microcontrollers, CAN drivers, and other ICs that can go through the same process. And then you look at immunity, right? And there are several such models that are necessary. And then you look at the bigger picture of models, right? Today we are generating IC models. Soon you can think of ECU models that will fit into the system level simulation. So all of this will require, I think, just trying to solve it with physics may not be feasible. It may be attractive, and understanding the physics is extremely critical, but some information, like we are in engineering, right? Some of the information required to generate these models from physics may not be available, although we may understand the full physics. So therefore, a data-based approach in generating these models may actually mean our ability to solve this problem or not being able to solve this problem. So I will stop here. I think that's my last slide. Yeah, sorry. My last slide is the second problem in EMI EMC, right? Which is that in spite of the IC guys passing the component level tests, and in spite of the IC guys passing the component level tests, some of the tier ones are sometimes failing in the bench tests, and in spite of the tier ones passing in the bench tests, sometimes there are problems in the system, right? So the way it is organized today, right, testing, measurement-based testing may not be adequate if you're looking at very complex systems, the complex systems of tomorrow, right? And this is in line with something, that is emerging slowly in the, well, not slowly, I would say quite fast, in the electronic design automation community. It's called model-based systems engineering, MBSE, model-based development, MBD. It is not only in EDA but also in system design. Some of these concepts are used. So let's say I was particularly impressed by one of the talks given in the same ECE webinar several months back, right? And you see a system like, let's say you're sending a rover, right? It contains electronic problems or electrical problems, thermal problems, mechanical problems, and so on. How do the teams interact with each other? How do the mechanical teams convey information to the electronics teams and the thermal teams, right? If I drill some holes on this system, that may have adverse effects. When it comes to electronics, it may have good effects when it comes to mechanics, right? So this way of studying, this model-based way of studying, has been extremely useful for us in scaling engineering. If you think about today, right, the way systems are delivered, you start with device physics at the very bottom, device physics, right? And then there are some engineers on the top level that are making gates and they're making cells and all that. The way we have been able to do this as a community is that the device physics guys have been giving us models of the transistors. These models, transistors, go into SPICE. Then we do some simulation and we get gate level models. So different levels of abstractions that has been enabled by models. So far, these models have been predominantly built using physics, right? And what we are trying to say here is that there's an opportunity to build some of these models using data as well. I'm pretty sure it's been done in several different industries and even in our industry, some of the places where I do not know about. But there's definitely a chance of solving some of the problems that are unsolved today using such a model-based approach and such a data-driven model-based approach. Yeah, I'll stop here. Thank you so much for your time and listening. Happy to answer questions that you may have.
Okay. Thank you, Dipanjan, for the interesting talk. I think there are a few questions already. So I think Aditya raised his hand. So Aditya, do you want to unmute and ask?
Yeah. Hi, Aditya here. Dipanjan, fantastic talk. Really enjoyed seeing the application all the way down to reality. I was curious about the, you showed those plots for, predicted frequency response and measured frequency response in many instances. So is it, they have, as far as the original problem goes, is it about, so you have an IC, you basically don't know anything about it. It's like a black box. Maybe you postulate that it is some, bunch of voltage sources or whatever, some parametric model. And then I suppose the aim there is to predict what waveform, either time or frequency domain, would result when you apply some controlled currents or voltages from outside, I guess, right?
Yes.
Right. So this measured waveform, is it spatially uniform, or is it? Do you consider it? Do you also care about in what direction what is radiating, or it's just at some typical point?
It is at a typical point. So, for example, right. So let's say we have a PCB, right, and an IC sitting here, right. What we are trying to do is to kick out this IC, right, and replace that with the model, right. And the model actually, it so turns out that some of the pins are quite benign. They're not doing any switching. So you are basically sort of saying this pin is switching and this pin is switching. Let me attach a voltage source at this pin and let me attach a voltage source at this pin, right? So there is no spatial part to it, but there is a time varying part to it, right? So this waveform will look like, like a typical switching kind of a circuit, right? And
it's a high dimensional sort of regression problem, the way I see it, where you want to try to adjust internal parameters of this two source system, let's say, such that you match the output waveform that you would actually measure, right?
Correct. Exactly.
Either
right?
time or frequency, I guess.
Correct. Exactly. That is exactly this. So basically the point is, how do you predict a waveform as a function of, let's say, 5 variables,
Very good. Okay. So then my question was the frequency domain responses you showed, they all had some basic structure. They were all periodic, with some spikes at intervals that slightly changed somewhat. They get more compressed and so on. Can you explain the reason for this kind of structure? Is it something natural?
Yeah, it's because of the periodicity of the waveform, right? So because the switching is happening very periodic, right? And that's why the structure in this, right? So that's why, looking at this frequency domain image, just like frequency domain picture, just like an image, may not be adequate, right? So there is some physical structure to this or mathematical structure to this. This is basically FFT of a periodic waveform with ringing and so on. So there is some structure to this.
I see. So there is some compression happening towards the right part, right? If it were uniform, then it would be essentially the FFT of a purely periodic signal, right?
Correct, exactly.
But I guess
right?
you're saying some other, some compression, some other phenomenon is also happening.
Yeah, it's the ringing that's happening, right?
Ringing.
So if you start off with like just a clock pulse, right? We know the FFT of that. Then you introduce the rise time and the fall time, right? That will give you a different FFT. And then you introduce the ringing, and what you see here, the part that you were pointing out, right? That is actually coming from the ringing, right? Some actually not this one. This is actual switching frequency, right? But some parts at the high frequency come from the ringing. I may not have that picture of the ringing. So all of these sort of have an effect, right? But it's at the end of the day, it's periodic. So we got lucky because then we sort of could predict the one waveform feature. Now there are some complications, right? Sometimes what is used is something called spread spectrum modulation, right? So in that particular case, one waveform is different from another waveform, right? So there are some complications, but in general, right now what we can handle is basically a single pulse and then periodic, same thing repeating over time.
Okay, great. Thanks.
Thanks, Aditya.
Okay. Any other questions for Dipanjan? I think Naveen has a question.
Yes, hi Dipanjan. Yeah, great talk. Thanks a lot. It was very interesting. So you're like, so there's of course, like as you mentioned, there's a difference between or you're trying to incorporate machine learning into these data-driven kind of models. Whereas there is also but there's also possibility of there is also a possibility of incorporating learning algorithms into physics-based solvers, right? So yes. I'm assuming that people look into it. So you can always, people do solve. There's a growing community, a growing amount of work in solving partial differential equations using neural networks. Is there already work or in this area wherein they try to solve Maxwell's equations within a complex environment, but using neural networks?
Yeah, I think not neural networks per se, but I think some folks have tried to. So what we see, what I have seen in literature, right, is that some of these, if you're able to, let's say typically the structures that we simulate, right? If you are able to parameterize the structure, so that's kind of very basic, right? So you predict, you identify some parameters and then you solve some and then you keep the rest for predicting. That's what I have seen. It's typically used, for example, VR dimensions in PCBs and trace width and trace length and all these different parameters. I've seen that work in literature. In fact, in our group itself, you talked about using physical, but you're probably talking more about solving the matrix equation, like a PDE or an IE-based matrix equation using some learning-based methods. That's a very favorite topic of mine, right? Because I think that's one of the ways we can actually make it work. The challenge here is in the electromagnetic domain, the challenge is the close coupling between every object to every other object, right? So everything interacting with everything makes it, a sort of a multi-agent problem with coupling with, every node connected to every other node, which makes it hard. What we had tried to do is that, typically these solvers use some Krylov subspace-based iterative techniques. So you kind of go down in terms of your error, like a typical iterative solver procedure. What we were able to do is that learn from structures that have been solved before and harvest that Krylov subspace and use that in converging faster, right? But that sort of still remains in the technology domain. It has not been, we've not been able to scale that very well. But these are the two approaches that we have seen. One of them from elsewhere is parametrization. The other one is direct solving of matrix, because I'm aware of this because it happened in my group, right? But still, I think there is some gaps here that the weather guys have done a great job in moving from completely physics-based model to some data-driven model. I think that has yet to happen in electromagnetics.
All right. Yeah. Thanks.
Okay. Any other questions? Okay, I had a more general question. So when you show this comparative data, right, from simulation and the experiments, do you or the end user, would they require some kind of a metric or something to say that
Yes.
there is good agreement, or are there standards?
Yes, so that's a very good point, Varun, right? So typically, right, there is an IEEE standard called Feature Selective Validation, FSV, right, by Alistair Duffy. That's an IEEE standard now of comparing two images, right? In this particular case, right, what I've seen people typically do is the first few harmonics, the first 5 harmonics, exact values, and then the envelope of the rest. So it's still not numeric. FSP is a complete numeric method in which you can actually come. And in fact, I met Alistair, and he was saying that in his PhD he faced upon a problem of how to sort of represent his data, how to represent his accuracy of his results, and then he came up with this technique called FSV. It is an interesting technique, and I think that's one that we did look into, right? But in general, in the industry, they don't really do FSV today. They look at more sort of commonplace things like the peaks at the harmonics and the envelope of the rest.
Okay, thank you. Any other questions from the students? Okay, looks like there are no other questions. So let's thank Dipanjan once more for the very interesting talk. And also thanks to all the audience for attending this webinar.
Thank you. Thank you so much. My pleasure.
Very good. And I think the next webinar we'll have in April, middle of April. Sorry, middle of March. Yeah. So see you all in the next webinar. Right? Okay. Thank you. Bye.
Thank you, Varun. Bye-bye.